For this lab, I studied the motion of a falling object. Newton's second law was still used, but unlike the previous experiment, F net was not zero and the velocity was not constant. The final and initial velocities were still measured in meters per second, the net force was measured in newtons, the mass was still in kilograms, and the delta T was in seconds. Again, I chose to film a tennis ball. In retrospect, I probably should have chosen a lighter object, for reasons I'll discuss later. The tennis ball was measured again at approximately 6.7 centimeters in diameter, which in meters is given as 6.7 times 10 to the negative second power. In the experiment, the ball was dropped in the negative y direction, but in tracker motion it came out horizontal, so I rotated the axis to reflect its original path. It started from rest, meaning initial velocity equals 0. At the origin, meaning initial position also equaled 0, the ball was dropped and began to descend towards the floor. The clip was shortened to cut out the initial ball holding and the bounces following its collision with the ground. Some points may have been lost due to the blurriness of the motion, but it did fall in almost a straight line. From this data, I made a model of the motion in Python, keeping the mass of the ball the same as my last experiment at 0.057 kilograms. Delta T was also not changed. The time was changed to reflect the length of the video. In the first motion model, F net was chosen to be only equal to the force of the weight, which is given by mass times gravity, defined as 9.8 meters per second in the negative y direction, multiplied by the unit vector of motion given by j hat, all of which were defined earlier in the code. J hat in this experiment was the direction of motion, y. F net was set equal to the weight force, and the code was run and the data saved. For the next model, the force of drag was added. First, Fd was defined as the constant b, which accounts for turbulent drag from the air, chosen negative to reflect the negative direction of motion of the force, multiplied by the magnitude of the ball's velocity and the direction of the motion held within ball.vel. The b constant was chosen by picking a random number and running the code, then checking to see how the final position compared to the final position of the experiment in tracker. Then the new net force was set equal to the previously defined weight force added to the new drag force multiplied by the unit direction vector. When run, this is the code shown. While originally we were supposed to model the turbulent drag force by an upwards arrow, the B that I chose was so small that the arrow does not show up if you use the correct, if you use the B constant that best fits my model. When shown on the same graph, the data given by these models shows some interesting things. Somehow, the two computational models overpredicted the ball's motion. They also seem to be virtually the same line. This may be due to the very small b I found when doing my calculations. This means air force was practically negligible when comparing the last two lines. This also accounts for why the drag arrow is not seen in my model, even though the code accounts for drag and it was seen with other b values. It was mentioned that the frames per second setting may be at fault for the overpredicted values, but I filmed in high light against a light-colored background to minimize problems with this. Because terminal velocity is the velocity when the upward, drag, and downward gravitational forces of a falling object are equal to 0, it would be impossible for the first model to show this phenomenon because it only accounts for the gravity force. The second model, however, could very well show terminal velocity because it accounts for both forces. Throwing the object down would change this velocity, as the ball would not begin at rest but with an initial velocity. If it were changed to, say, -10 newtons, this would have been the result of the model. As you can see, the ball moves farther in the same amount of time, and, although you cannot see the arrow, the ball would begin with drag as well.